Okay, section 3.5, video 2, just one more example. Another rational function here that we're going to try and sketch. Let's go through the basic things that we need. We need the domain. And the domain of this one, well, if you look at this, x squared plus 1 is in the denominator. Nothing's going to make that 0. So the domain here is all real numbers, notated with that capital R with the extra line through it if you've never seen that before. But of course, since nothing makes the denominator 0, that also means that there are no vertical asymptotes, which is kind of nice. We've already taken care of that. Since nothing makes the denominator 0, excuse me, that also means that there are no holes, which we actually did not talk about in the previous one, but a hole is what makes both the numerator and the denominator 0 at the same x value. Let's see, horizontal asymptotes. Let's just go ahead and go through some of this. I know I'm not necessarily going in the same order, but well, the growth rate on the numerator is greater than the growth rate of the denominator, so that means that there's also no horizontal asymptotes. So we'll say none. But the numerator's growth rate is exactly 1 power higher than the denominator's growth rate, which means that we do have a slant asymptote. Oops, not stant, slant. So we are going to have a slant, and we'll figure that one out in just a minute. Let's go ahead and talk about intercepts. X-intercept. The x-intercept is what's going to make the numerator 0. Well, the only thing I can plug into the numerator to make it 0 is 0. The y-intercept is what you get when you plug zeros in for all the x's, and in this case, that's going to be 0 over 1, which is also 0. So we end up with the x and y intercepts, again, just being at the origin. All right, we do have to figure out our slant asymptote. So to figure out the slant asymptote, we're going to do a little bit of long division. So remember, we're going to have to put the x cubed on the inside. We do need all of the terms down to the constant term, so I don't have any x squared, so I'll make it 0x squared. I don't have any x's, so I'll make it 0x, and I don't have any constants, so we'll just say plus 0. On the outside, we do need to include all the placeholders. So we're going to have x squared, but I don't have any x's, so we'll write 0x and then plus 1. If you remember, the concept here is, what am I going to multiply by the first term out here, which is x squared, to get x cubed? Well, that means I have to multiply it by x. So I'm going to put an x up here, then distribute the x to everything on the outside of the division sign. So that's going to give us x cubed plus 0x squared plus x. Just like regular long division, then I will subtract. X cubed minus x cubed is 0. 0x squared minus 0x squared is also 0. And then 0x minus x is just minus x. Okay? There is nothing that I'm going to, well, it's not true. I'm not going to multiply any polynomial times x squared to get x. I can bring down to 0, but it won't matter. So that's it. My equation is y equals x. That's my slant asymptote. We don't ever have to worry about the remainder, which is what you would really have here. You'd have negative x on top of x squared plus 1. The remainder won't matter for the slant asymptote. It's just a linear equation without its remainder. Okay, so we've got all those pieces. Now let's find derivatives. Let's go with blue on this one. So y prime is going to be, let's see, the derivative of the top, 3x squared times the bottom, x squared plus 1, minus the derivative of the bottom, 2x times the top, x cubed, all over x squared plus 1 squared. Let's simplify. So on the top, I'm going to get a 3x to the 4th minus a 2x to the 4th. So I'm going to have an x to the 4th plus a 3x squared after distribution. Pretty sure that that's right. And then on the numerator, on the denominator, we're just going to still have x squared plus 1 squared. All right, so we're going to have to figure out what makes the numerator 0 or what makes the denominator 0. Well, if you're looking at this carefully, there's nothing that's going to ever make the denominator 0. X squared plus 1 at the very least is always 1 1 squared is going to be 1. That's the smallest value that x can ever be, and excuse me, that the denominator can ever be. So it'll never be 0. So really we just have to focus on the top, which means x to the 4th plus 3x squared equals 0. I can factor out an x squared, and then we get x squared plus 3 equals 0. The x squared plus 3 in parentheses, that once again, that can never be 0. The smallest that will ever be is 3. But x squared on the outside can be 0 when x is 0. So that's the only critical value that we have. So let's put x equals 0. We're going to test values into our most simplified version, which is probably this. If I plug a -1 on the top, because I'm raising -1 to the 4th and to the 2nd, they all become positive. So the numerator is positive. The denominator is always positive. So it's positive, increasing. If I were to plug a +1 on the numerator and denominator, once again, I get all positive values. So it's an interesting function in the fact that it's constantly increasing except at 0, which must mean it levels off for just that 1 split second and then starts to increase again. All right, now let's figure out our second derivative. So I'm going to go from the simplest version, which is, again, this one. So the second derivative is going to be a mess. Let's see. Derivative of the top, 4x cubed plus 6x times the bottom, x squared plus 1 squared minus derivative of the bottom. Again, one bit of a chain rule here. So 2x squared plus 1 to the first power times the derivative of the inside of that parentheses, which is 2x, times the original numerator, x to the 4th plus 3x squared, all over the denominator squared. So now to the 4th. All right, I definitely want to clean this up. It looks like a real big mess, which is what I thought it would be. We can get rid of one of the x squared plus 1s from all the different terms. So from that term, get rid of one of those from there, get rid of one of those from there, leaving us with 3 of them. Any way we look at this, it looks like we're going to have to end up doing some foiling. So foiling the 4x cubed plus 6x times x squared plus 1 on the first one is going to give us 4x to the 5th. That's the first. Outside is going to be 4x cubed. Inside is going to be 6x cubed. So we're going to get plus 10x cubed. And then last times last is plus 6x. All right. Now we're going to, at least we don't have to FOIL anything in this last part here, because I'm going to multiply these two things together and then distribute that into here and here. So we're going to have a 4x, or excuse me, a negative 4x distributed in. So it's going to be a minus 4x to the 5th, and then a minus 4 times 3 is 12. So minus 12x to the 3rd, all over x squared plus 1 cubed. Okay, let's continue to simplify. 4x to the 5th minus 4x to the 5th is gone. That's nice. 10x cubed minus 12x cubed gives me a minus 2x cubed. And then I still have a plus 6x over x squared plus 1 cubed. So again, the denominator here is never going to give us 0 because I've got x squared plus 1 on the inside. Even though I'm cubing it on the outside, I can't get a negative value or a 0 on the inside. So that will never be undefined. The numerator, however, can. So I'm going to take negative 2x cubed plus 6x and set it equal to 0. Factoring out a negative 2x is going to give us x squared minus 3. So it looks like x is either going to equal 0 from the outside piece, or x is going to equal the plus or minus square root of 3 from the inside piece. Okay, that's not really the nicest of numbers there, but those are the values that we have to deal with. So let's set up our number line, our second derivative number line. Negative root 3, 0, and positive root 3. All right, the values that we plug in are going to go back into probably this one right here. Remember that the denominator here will never be 0. As a matter of fact, it's always going to be positive because I'm taking x squared plus 1, so that's positive, and raising it to the third power, it's still going to be positive. So really the numerator is going to determine everything. So really I might want to look at this piece because that's the numerator. So let's see what happens. If I take something less than negative square root of 3, well, square root of 3 is about 1.7. So the negative of that's negative 1.7. So if I plug negative 2 in, I'm safe on the left-hand side. Plugging a negative 2 in is going to give me negative 2 times negative 2 on the outside, so that's positive. Negative 2 squared is positive. 4 minus 3 is 1, so that's positive. So I'm going to get a positive times a positive, which means concave up. And then something in between negative root 3 and 0, like negative 1, is going to be positive on the outside, but it's going to be negative on the inside because you're going to get 1 minus 3, which is negative 2. So positive times negative is negative, so now it's concave down. Something in between 0 and root 3 is 1, so that'll be negative on the outside, negative on the inside, so that's positive. And then greater than square root of 3, like 2, is going to be negative on the outside, positive on the inside, so negative, so concave down. Remember that there were no undefined values, so you've got inflection points at all three of these things. So I've got inflection points at the negative square root of 3, 0, and the positive square root of 3. All right. So finding your inflection points is a little more challenging. The 0 one's easy. That's 0, 0. If you plug that back into your original function, that's easy. If you plug square root of 3 or negative square root of 3 back into the original, what you'll see is you're going to get out exactly the opposite values. So basically, that means that this is going to be an odd function, which I didn't actually test for before, but it will be. And if I plug back in the negative square root of 3, I'm going to end up with the negative 3 square root of 3 over 4. And if I plug in the positive square root of 3, I'm going to end up with 3 square root of 3 over 4. You can go ahead and double check that. So that tells me I have inflection points where the concavity is going to change. Let's see if we can actually sketch this thing. It's a very interesting graph. There's y, there's x. All right, again, plot my points first. I know I've got a point at the origin. It is not a maximum or minimum because it goes from increasing to increasing, but it does level out to a slope of 0 at that one point. The only other points that I know is that I know my inflection points. So I've got an inflection point at 0, 0. Well, that's already on there. I've also got an inflection point at square root of 3, comma, 3 square root of 3 over 4. I don't know exactly what those are. Square root of 3 is about 1.7. 3 square root of 3 over 4, I don't know, it's someplace up here. Someplace in that range. I don't know exactly what it is. Going the other way, I'm going to have the negative square root of 3, negative 3 square root of 3 over 4, so someplace right about there. The only other thing that I do know is that I have a slant asymptote, which is y equals x. So it looks something like that. There's your slant. So what I do know is that the function will approach the slant asymptote as we start to go further and further out on the x-axis. Let's check all the concavities and everything. It's always increasing, but it says that it's concave up until we get to that first inflection point. So in order for that to work, the function has to be coming along here and increasing, but it's got to be slowly bending up to that inflection point. So it's concave up, but then it's concave down until it hits 0, but still increasing. It's got to be up, still increasing until it hits 0. Then it levels out for 1 second. Then it's concave up again. Well, this is kind of making sense. Concave up, so bending up into that point. And then it's supposed to be concave down, but still increasing. So now it's going to start to bend down, but approach the asymptote. So it looks something like that. Very interesting looking function. All right, that is a lot of stuff for 2 problems. Hopefully that's plenty enough for you to get the understanding of what we're looking for graph sketching.